Hello everyone, I am Rubaya Ruman. Today I'll present my paper submitted to the Civil Infrastructure and Construction Materials 2023 conference titled Wood Ash Based Low Carbon Cementitious Composites. So the outline of my presentation is the following. First, I'll discuss about the background of my research study, and then I'll talk about the experimental program, including the testing protocol and the material characterization test results. Then I'll discuss the results of the mortar mixtures, for example, the setting time test results of the cement paste, and then the composite strength test results of the mortar. And then I'll talk about the statistical analysis of the mortar mixture composite strength results. Then I'll talk about the conclusions and recommendations. To give an overview of the background of this research, I would like to highlight the carbon dioxide emission per category illustrated by this pie chart, where you can see that concrete solely is responsible for 8% of the total global emission, and the main responsible ingredient is cement production. Cement production emits a lot of carbon dioxide because of the calcination of limestone occurs at a very high production temperature, and 1,000 kg of cement production emits 900 kg of carbon dioxide, which is a lot. To reduce the carbon dioxide emission of cement production, supplementary cementitious materials or SCMs are used. These are some examples of SCMs, for example, ground granulated blast furnace slag, lime, silica fume, coal fly ash. These have hydraulic and pozzolanic property. Hydraulic property is a property of cement, the binding and strength giving property of cement, and pozzolanic property is the reaction with calcium hydroxide produced by hydration of cement to form secondary hydration products. One of the most popularly used supplementary cementitious material is coal fly ash, which is of two types, Class C and Class F. Class C has both pozzolanic and hydraulic properties, and Class F is mostly pozzolanic property, and according to the classification of ASTM C618. Addition of coal fly ash improves the durability of the concrete. It reduces the cost of the construction, improves the workability of the mortar and concrete, and gives later edge strength. And also, of course, it reduces the concrete's carbon footprint and it is replacing cement. However, coal fly ash comes from coal power plants, and burning coal is highly greenhouse gas intensive process. Hence, coal industries are being shut down all over the world. So we need a potential substitute of coal fly ash. So can wood ash be a potential substitute? Wood ash comes from the timber-based construction industry, and it has severe disposal issue. So for example, Tolko Industries, which is our industry partner, is situated in Armstrong, British Columbia. It self-produces 20 tons of this ash every day. There are two types of ash produced. One is wood fly ash, which is finer in size, and one is wood bottom ash, which is coarser in size. So we used wood fly ash to replace cement and wood bottom ash to replace sand. So the materials used in this study are the general use cement, wood fly ash, sand, and wood bottom ash. To talk about the experimental program, the material testing protocol is this, where since it's a new material, both the wood fly ash and wood bottom ash, so it needs to be characterized. So on the ash, the particle size distribution, natural moisture content, bulk density, pH, and oxide composition was determined, and specific gravity, absorption capacity, and sieve analysis were done on sand and wood bottom ash. So these are the mixture details of the mortar. So wood fly ash replaced cement at 0, 15, 30, and 45%, and wood bottom ash replaced sand at 0, 15, and 30%. So these are the results of the physico-chemical properties of wood fly ash. So from the particle size distribution, you can see that it's quite coarser in size compared to regular coal fly ash. And its pH is in the range of 10 and 11, which means that it's alkaline in nature. So this graph shows the oxide composition found from the XRF test result of wood fly ash, class C coal fly ash, and GU cement. So the most prominent ones are the calcium oxide, silica, and alumina. So you can see that calcium oxide, of course, is the highest for cement, but also for coal fly ash and the wood fly ash, it's in the range of 25 to 27. So if calcium oxide is greater than 18%, then according to STMC 618, its chemical composition is close to class C coal fly ash. And in the silica content, you can see that it's low for cement, but for wood fly ash and class C fly ash, it's higher. And also there is alumina, which is also the highest is found for class C coal fly ash, and cement has the lowest. This figure shows the gradation of sand and wood bottom ash, and you can see that it follows the upper and lower limit of the CSS standard. These are the properties of the sand and wood bottom ash, the specific gravity and absorption capacity. And from the fineness modulus result, you can see that sand is finer. The sand that we used were finer than the wood bottom ash that we used. So this graph shows the setting time test results, both the final and initial setting time results of the cement paste of the corresponding mortar mixtures. And you can see that compared to the reference cement paste, the 15, 30, and 45% wood fly ash replacement did not affect that much. I mean, there is no trend. So since its composition is similar to the class C coal fly ash, and class C coal fly ash is less pozzolanic and more hydraulic, it does not affect setting time that much, and which also occurred in case of the wood fly ash. This figure shows the composite strength test results of the mortar mixtures, and both the wood fly ash and the wood bottom ash decreased the composite strength result compared to the control mortar. And however, the composite strength results were quite comparable with the control mixture, up to 30% of wood fly ash replacement. The decrease in composite strength for the mortar mixture for F15B0 and F30B0, which means 15% wood fly ash, 30% wood fly ash, and no bottom ash, were 9.3 and 16.6% respectively, which we can say is quite comparable. And for F45B0 is the strength reduction is 54%. The compressive strength drop for 15% wood bottom ash replacement for 0, 15, 30, and 45% wood fly ash were 3, 14, 62, and 77% respectively. And compared to the control specimen, of course, and 30% wood bottom ash replacement reduced the compressive strength by 18, 33, 70, and 77% respectively for 0, 15, 30, and 45% of wood fly ash. So two-sample t-test approach was applied to analyze the compressive strength test results in order to find if there is any significant contribution of the wood fly ash and wood bottom ash on mortar compressive strength. The p-values greater than 0.05 means that the null hypothesis cannot be rejected, which means that there is a significant difference in the mean values of the samples. All the values in the first table are lower than 0.05, which means that the addition of wood fly ash in the mixture has a statistical contribution, all of them. And the highest p-values were observed when the comparison was made between 15 and 30% of wood fly ash replacement. This signifies that the highest variation in compressive strength was observed for the mortar with wood fly ash replacement of 30 and 45%. The average compressive strength value at 28, 56, and 91 days of curing range were also compared and shown in the next table. And you can see that some values were highlighted, which are greater than 0.05. So at 15% wood fly ash content, there is no significant difference in the mean of the mortar samples with 0 and 15% wood bottom ash. Similar results were observed between the wood bottom ash replacement levels of 15 and 30% for the 45% wood fly ash level. Also, at no wood fly ash replacement level, there is no significant difference in the average mortar composite strength between 0 and 15 and 15 and 30 at later curing ages, for example, 56 and 91 days of curing age. So to conclude, the chemical composition of the wood fly ash resembles that of Class C coal fly ash. And just like Class C coal fly ash, wood fly ash had little or no effect on the setting time of the cementitious composite as when used as an SCM. The compressive strength of the cementitious composite decreased with the increase of both wood fly ash and wood bottom ash. However, the mixture containing 15% wood fly ash and 15% wood bottom ash showed promising results, which actually reduced the compressive strength by 14.9% compared to the control. And the statistical analysis by two sample t-tests showed that there was a significant contribution of wood fly ash on the mortar's compressive strength, and wood bottom ash showed significant variation in the average compressive strength for all the percentages and all the curing ages at the 30% level of wood fly ash replacement. So future research shall compare the results with other mixes or alternate materials. For example, Class C fly ash, Class F fly ash will be compared with different types of wood fly ash and wood bottom ash, for example, high temperature and low temperature wood fly ash. And also the source of the wood fly ash is very important. For example, the trees, the type of trees, and also the seasonal variation is important on the properties of the ash. It will also be studied, and life cycle analysis will be also included in the study to see how it affects is environmentally, and also life cycle cost analysis will also be done. So thank you everyone for listening to my presentation. I'd like to thank my research lab, Alam's Lab, Applied Laboratory for Advanced Materials and Structures at UBC Okanagan. And I'd like to thank our industry partner, Tolco Industries, Fodry Homes, and M&K Ready Mix Companies. I'd like to thank NSARC and also ACI for their support and contribution towards my PhD research. So thank you everyone for listening to me. If you have any questions, please, you can ask me through email. I'd be happy to answer you if you have any queries regarding my research.